Hi, and welcome back to this video. Um, Today we're going to be doing confidence intervals with the normal distribution, and the next lecture is also going to be about confidence intervals, but we will discuss the t-distribution. So let's get started with an example from a previous lecture that we all know how to do, but this is just a review here. A hospital is conducting a study to monitor the average systolic blood pressure of a population. They randomly sample 100 adults and measure their blood pressure. Based on prior research, the population mean systolic blood pressure is estimated to be 120 with a population standard deviation of 15. So we're given three numbers here that are all important. We have the sample size n, we have the mean of the population, we have the standard deviation of the population. Calculate z-scores that cut off the middle 90% of the sampling distribution, the middle 95% of the sampling distribution, and the middle 99% of the sampling distribution. Now we're working with a sampling distribution because we're sampling 100 adults here. So let's take a look at how we do this with the calculator. The function that we use when we try to find z-scores, but we're provided with the area, remember, given area, but trying to find the z-scores or the raw scores, the function that we use on the calculator is inverse norm. So we're going to go to the calculator's inverse norm function, and let's also remember, the central limit theorem is helpful here because our sample size is 100 and that is greater than 30. We automatically have a normal distribution shaped sampling distribution. So because it's normal shaped, we can use IMV norm. So to go and figure out the z-scores that cut off the middle 90%, use IMV norm. And remember when we're using z-scores, our mean is 0 and our standard deviation is 1. And we're going to round this to 3 decimal places. So this is the area that looks like the middle 90%. And the question is asking us to find the two z-scores that cut off that middle 90%. So that would be the lower end and the upper end of this shaded area. So we go to inverse norm, and I'm not going to open my calculator right now, but to get to this number, to get to this function, you type second and then distribution, and this is number 3. The area you're going to enter is 0.90 for 90%. Use your mean and standard deviation as 0 and 1 for the middle z-score and the standard deviation of z-scores. And for tail, you're going to press center and hit paste. And that's going to give you two z-scores. We're going to round these two numbers to 3 decimal places. Okay, so we're going to take up to the 4. Now take a look at the number after the 4. In both cases, it's an 8, so we're going to round that last 4 to a 5. So we have a negative z-score because when we're on the left of 0, it's negative, and we have a positive z-score. When we're on the right side of 0, the z-scores are positive. So the two z-scores that we find here are negative 1.65 and positive 1.6. I'm sorry, I said 1.65. I meant 1.645 and positive z equals 1.645. Now, what's going to happen when we increase that area to 95? So let's take a look at the area now. When we increase it to 95, the picture widens, the area in the center widens, and so the z-score that we're looking for on the left and the right are going to be further away from 0. So in the calculator inverse norm again, we're going to put in 0.95, 0, and 1, and choose the tail to be center. And when we do this, our two z-scores are further away from 0. 1.9599, 1.9599. We're going to round this to 3 decimal places, but when we round the 9 up, it becomes, this 59 becomes a 60. So it's negative 1.96 and positive 1.96. Now, if you don't have this calculator that has the tail option, if you're using the old calculator, I did supply instructions on how to do this, but honestly, to do most of the work in this lecture, you are not going to need to revisit inverse norm. I'm going to show you a different approach. So the use of inverse norm here at the beginning of this lecture is only for introductory purposes. We're going to not be needing this again. We're going to remember these z-scores though, because they are going to come in helpful a little bit later. We're going to do this one more time with an area of 0.99. Now notice the picture changes even further. The area looks like it's almost filling in almost all of the bell curve. Let's find those z-scores that cut off the middle 99%. So for area, we're going to put in 0.99, mean 0, standard deviation 1, and again, tail center, paste, and our two z-scores now, negative 2.57, and we're going to round this up to a 6, and positive 2.57, and then round this up to a 6. 2.576 and negative 2.576. So these sets of z-scores for, this was the 99, middle 99%, and we had the middle 95% and the middle 90%, are going to become part of confidence interval formulas that we are going to be using a little bit later. Okay, so let's remember them. You can always have these on hand on a piece of note paper or somewhere on your computer that you can reference. The middle 90% z-score cutoffs are negative 1.645 and positive 1.645. The middle 95% z-score cutoffs are negative 1.960 and positive 1.960. And the middle 99% z-score cutoffs are negative 2.576 and positive 2.576. I'm going to take a little detour for a moment to talk about some data that's collected by the Gallup organization. And this data is available online. I'll share the URL in a moment. Positive and negative experience indexes are statistics that are calculated at the Gallup organization. They reflect people's daily experiences, and it's done globally. The data is collected globally, so we get a number that represents the world. These indexes track the world's experiences with pain, worry, stress, anger, enjoyment, laughter, and more. And what you're looking at here are line graphs that go back to 2006 and the last one here is in 2023. And we have, at the start of this data, we have a positive experience index of 68 and up at the end, 71, so it went up, and a negative index of 24 in 2006, and it went up to 31 here. So how is that data calculated? How was it gathered? Here's the URL that you can visit if you want to read more about how this is analyzed. But in short, I'm going to summarize for you. Indexes are calculated from surveys in more than 140 countries. Results are based on telephone or face-to-face surveys of approximately 1,000 or more respondents in each country. So these are surveys, which means that we're not looking at the entire population. We're just looking at a sample of the population for this data. The following items make up the positive experience index. These scores strongly relate to people's perceptions of their living standard, their personal freedoms, and the presence of social networks. So these are the items: well rested, respected, smiled or laughed, learned or did something interesting, experienced enjoyment. These factors are parts of the questions that Gallup asks its survey participants, and the answers are gathered and built to create the well-being index. There are also negative experience index numbers as well, and those are measured from people's pain, worry, sadness, stress, and anger. So we're going to focus on the positive experience index. I'm going to show you some of the charts that make up these factors for the positive experience index. For each survey question, like, did you feel well rested yesterday? The answer is either usually yes or no. So Gallup finds the percentage of all the yes answers. For example, we have a few questions. Did you feel well rested? Did you feel respected? Did you smile or laugh? Did you learn or did something interesting? Did you experience enjoyment? So all the yes answers are tabulated, and the percent of people answering yes to those questions is constructed. And we have 5 percentages. Now, the average of those 5 are then calculated, and that makes up the entire positive experience index. Now, on the first slide here, the picture of the initial graph, let me go back for a moment. The positive experience index is 71, and this is exactly how it gets calculated. The individual indexes are calculated, and then the average of those index is calculated, and that gives us a number close to 71, and that's the positive experience index. The same is done for the negative experience index, but I'm focusing on the positive one right now. So each of these is a question, and each of them are each of these percentages are calculated separately, and we also have a visual for each of those through the years as well. So a person would be asked, did you feel well rested yesterday? This is the data in a visual form. So here's the question that gets asked to the individual taking the survey. Now, please think about yesterday from the morning until the end of the day. Think about where you were, what you were doing, who you were with, and how you felt. Did you feel well rested yesterday? And how the person answered yes or no is used to construct the index for feeling well rested. Now, if you take a look at where things were, it looks like they were at their highest in 2010, and 2006, it looks like it's low also, and also low in 2021. Okay, so this is for feeling well rested. We have these for all 5 of those positive experience components. Treated with respect. Were you treated with respect all day yesterday? And you see, this definitely went up over the years from 2006, around 80, to 2023, around 85. And then we have, did you smile or laugh a lot yesterday? It looks like this data took a dip in 2020, which we all remember was the pandemic. And then, did you learn or do something yesterday? And this looks like it's increasing over time. It took a dip in 2017, but it looks like it's steadily gone up since 2006, so 54. So all of those, there's one more. There's, did you experience enjoyment yesterday? And this seems to decrease over time from 75 to 73, with the dip occurring in 2021. So this is some interesting data to look at. And if you want to go and see how they and read about more on how they do this survey, you can look at this website. Okay. So now we're going to go back to a little bit of what we're going to talk about today. The percentage of people in 2020 who smiled or laughed a lot. So when we look at 2020 on this picture and we see approximately, we're looking at a value of 70. The percentage of people in 2020 who smiled or laughed a lot. But what you don't see in this picture is that Gallup provides more information. And I'm sorry, I'm going to go back to that in a second. Let me first ask you, the 70%, does this represent a statistic or a parameter? So let's review our terminology. A statistic is a number that represents a sample, and a parameter is a number that represents a population. So does this 70% here, does it represent a sample or a population? And it represents the people who answered the survey. That is a sample, and so this number is a statistic. 70% is a proportion of the sample. So this is what I was referring to before. There's more information that you don't see just looking at this graph. Gallup provides a margin of error, and the margin of error, and we're going to talk a lot about that today, is provided as plus or minus 2.2%. And the reason why it's indicated is because this is a sample, and the percentage of the sample may not be the same, exactly the same as that of the population. So 70% reflects the sample, but the true population percentage of people who smiled or laughed a lot may not be exactly 70. So we have this margin of error to account for that possible variation. Let's look at how we can apply that margin of error. Applying the margin of error gives us more than a single number, 70. It gives us an interval. An interval is a range with a lower limit and an upper limit. So if we take 70 and we plus or minus 2.2, that means we're going to both subtract 2.2 and add 2.2 to 70. So subtracting 2.2 from 70 gives us 67.8, and adding 2.2 to 70 gives us 72.2. And the interval is going to be the range from 67.8 to 72.2. The interval of people who smiled or laughed a lot in 2020 is 67.8 to 77.2. Now that's given to us because, again, the sample is only reflective of that sample. And while we hope it reflects the population, we can't be sure that the number for the sample is exactly the same as the number for the population. So let's look at some terminology here. Estimation involves using data from a sample to make educated guesses about values of unknown population parameters. So when we estimate, we don't necessarily know the percentage of people who felt well rested yesterday. It's unknown. So we are estimating it from our sample. When we estimate a percentage, we are estimating the proportion, and we could also estimate a mean, in which case we'd be estimating mu. The point estimate is the single value that's calculated from the sample. So if you have the sample and you calculate a sample mean, you're calculating X bar, and that would be the point estimate. If you're looking at your sample and you calculate the proportion of people who answered yes to the question, did you feel well rested yesterday? when you calculate a proportion, you're calculating a sample proportion, and it's symbolized by the symbol P with a hat on top. We call it P hat. Um, since most of our work in the previous few lectures have been dealing with sampling distributions involving sample means, most of our work today is going to be all about sample means. But the same kind of work we're doing in sample means can be used with sample proportions, which are also very, very powerful indicators and estimates for the population. They are best guesses for the corresponding population parameter. So when we take that point estimate and we find a range of values around it, we call it an interval estimate. It's a range of values. For example, a confidence interval, that's what we're going to call our range of values, within which the true population parameter is likely to fall, along with a level of confidence. So we're going to have a degree of confidence that's either going to be 90, 95, or 99%, and our interval estimate is a range of values that we hope the true population parameter is inside. So back to this example, this is a range of values, and we're not exactly sure what the population proportion is for people who smiled or laughed a lot. We don't know exactly the population proportion, but we're hopeful and we're confident that it's somewhere in this range. So it is an interval estimate. So let's look at the Gallup poll on emotional well-being. If 70% of the sample reports smiling, laughing in 2020, that's a sample proportion, and it is used to estimate the proportion for the entire population. That 70% is a point estimate. It's a single number. The interval estimate is the range that we calculated before, 67.8% to 72.2%. So why do we use samples instead of the whole population? Well, collecting data from an entire population is often impractical or impossible. A random sample provides a manageable data set that could yield meaningful insights about the population without necessarily surveying the entire population. How sample statistics work? A statistic like X bar or P hat is calculated from the sample and serves as an approximation of the true population parameter, mu, or P for the population proportion. So we've done most of our work with sample means and population means, and we will continue. Although working with the sample proportion, P hat, and a population proportion, P, are also very valid calculations that can also be done in the same way. Sampling variability means different samples yield slightly different statistics. But if we make our samples large, larger samples tend to produce estimates closer to the true population parameter. So what Gallup does, it surveys 1,000 people worldwide about healthcare costs. Oh, this is an example, I'm sorry. If Gallup surveyed 1,000 people worldwide about healthcare costs, the sample mean healthcare cost could estimate the global mean cost. So this is the crux of inferential statistics, using a sample to estimate a population. Statistical inference involves making generalizations about a population based on sample data, considering sampling variability and uncertainty. There are two main types of statistical inference that are coming up. Confidence intervals are right now. We're going to be doing confidence intervals for the next two lectures. And what we do in this topic, we create a range, an interval of values for a population parameter. So we don't know what the population parameter is. It's a question. It's an unknown. Hold on, let me get back to this. Okay, we don't know what the population parameter is. It is an unknown, but we create a range of values that hopefully the population parameter falls inside that range. And we're going to be developing confidence intervals and interpreting them with this kind of phrasing. We are 95% confident that the mean cost of delivering a baby in countries with public healthcare systems is from $2,000 to $5,000. That would be an example. The other type of statistical inference that's coming up that's really important is hypothesis testing. In hypothesis testing, we evaluate claims about a population parameter using sample data. Here's an example. We could test whether the cost of delivering a baby has changed compared to a previous year. So we would be using sample data, testing sample data, and then deciding whether or not the cost of delivering a baby changed. And where does this connect to a sampling distribution? Well, inference, statistical inference, relies on the sampling distribution of the statistic, which, as we've discussed, is the distribution of sample means if many samples were taken. So imagine, remember the central limit theorem told us that if we have a sampling distribution and we're wondering what its shape is, it will be approximately normal if the sample size that we used is large. So if n is greater than 30, I'm sorry, let's just say greater than, not greater than or equal to. Or if the population is normal to begin with, then we can also be sure that the sampling distribution will also be normal. So let's look at this picture. This was, I think I talked about this in a previous lecture. If we start with populations, most of the pictures here are non-normal populations, and we sample from that population, you could see that the normal population stays normal, but the other populations have an unknown shape. Only when n hits 30 do we start to see all of the sampling distributions look normal. And the rule that we're going to follow is that n has to be greater than 30 for us to ensure that we do have a normal shaped sampling distribution. We did this with the calculator Desmos. We did a visualization of this. We started with a population that was not normal. And you could see here, this green population looks a little skewed to the right. Okay, we took samples of size 10 from the population, and it kind of took on a shape that started to look a little bell-like, and here it would be to overlay it on top of the population. It kind of looked like this. It started to look a little bell-like, but it definitely wasn't bell-shaped. When we made n 30, it got to be more bell-shaped. And then when n was 80, it was certainly bell-shaped. In addition to its shape looking more and more normal, we also saw that its variability decreased. It got the range got shorter and shorter from the high end, the low end to the high end. So that's important to us. Let's do our first problem with confidence intervals. I'm going to take this one a little slow and explain everything every step of the way, but when we get to the next problem, we can move right into the solution. So we're going to start with a sample of 36 patients discharged from a local hospital, and the average of that sample is $2,630. And we're also provided with a population standard deviation for hospital stays, and it's 600. And that's supposed to be in dollars. Construct a 90% confidence interval to estimate the true average cost of a hospital stay for all patients at this hospital. So we're using inferential statistics. We're using our sample of 36 patients to give an estimate about the cost of a hospital stay for all the patients. Interpret the results of your confidence interval. So we're not provided with any raw data. We are given the X bar directly. So in some questions, we may be provided with raw data in which we have to calculate the X bar. Here, we're given the X bar. So what this question is asking us to do is to calculate an interval of values, a confidence interval, for which we are 90% confident that the true population mean cost of a hospital stay lies. Okay, that's what we're trying to figure out. The sample mean 2630 is unlikely to match the true mean exactly. So it's very unlikely that X bar that we calculated here and mu that we're trying to estimate, it's very unlikely that it's the same exact value. But if we construct a range of values around 2630, we can be 90% confident that it captures the true population mean. So this arrow represents money, time, average cost of a stay at a hospital, and our true mean is somewhere on that arrow. It's unknown. Okay, it's an unknown mean cost of a stay at a hospital. So what we can do is we take a sample of 36 patients, we calculate the average for that group, and that's our sample mean, 2630. Now around that sample mean, we're going to build an interval. So the interval is going to have a low and a high, and we are hoping that the interval captures what the true mean actually is. The yellow box provides a range of values around the sample mean. So our sample mean is our point estimate, and the interval is the range of values around the point estimate. The interval that we create, the yellow box, may or may not contain the true population mean. But when we finish this, we're going to be 90% confident that it does, that the true mean is in that yellow range. Why is it possible that the box does not contain the population mean? Well, let me show you why. Let's start with a picture of the sampling distribution, and let's have the true population mean. That's not GPA. That is not GPA, that is hospital stay cost. Just a minute. Okay, start with a picture of the sampling distribution with the true population mean hospital stay cost, which is unknown, in the center. So here's our sampling distribution. It is normal because n is greater than 30. And the true population mean is unknown. It's in the center. Now let's block off the middle 90% of all sample means. So we're going to have a low end and a high end to this piece of area. The horizontal axis contains all possible sample means, and these are just some. I'm just labeling some of them, but the horizontal axis would contain all of them. And our sample mean that we happen to get from our 36, our n equal 36 patients, our sample mean can be any point on the horizontal axis. So it could potentially be, let's make an arrow the length of the space between the low end of this area and the high end of this area. And let's use the same size arrow to build a range of numbers around each X bar. So potentially we could choose an X bar that is way off to the left, like this one. If we build an interval around that circled X bar, do you see how the interval, the low and the high, do not capture the true population mean, which is right in the center? So if we happen to pick this X bar, it would be a bad sample mean because it doesn't capture the true population mean when we create the interval. But if we do the same with the next X bar, okay, so let me erase the first marking I made. Okay. So if we make the range of values around the second X bar, well, now this arrow, this range that we create, well, take a look. It does capture the population mean. The population mean is inside that range. And if I do it for all these X bars over here, they also capture that true population mean. However, when we go too far, when we go past this border of the shaded area, now this X bar out here is too far away. The population mean is not captured in that interval, and the population mean for this X bar is not captured in the interval either. So I'm going to do it with a different color here. Population means The population mean is captured in intervals for the middle X bars, but when the X bar that we happen to choose is way off on the left or way off on the right, we fail. We don't get the true population mean. So we see that this happens 5% of the time because 5% of the sample means are in that rightmost upper tail. And here, 5% of sample means are in this lower tail. So in total, 10% of the time, we could potentially pick 36 patients that don't match what we need. We needed an X bar inside this range, and 10% of the time it happens, or rather 90% of the time that will happen, but 10% of the time it will not happen. And so that's why we say that we are building a 90% confidence interval because we have confidence that the X bar we choose will contain the true population mean 90% of the time, but 10% of the time it will not. Okay, so let's label the z-scores that we calculated in the beginning of this lecture at the far left and the far right of the shaded area. And these we're going to remember. We're not going to recalculate these every time. The standard error is labeled here in the center, sigma divided by the square root of m. That's a measure of the spread of the sampling distribution. We're going to be using that in our formula as well. Using the standard error and the z-scores together, we are going to determine the length of the interval, which is the blue arrow. And that's going to give us our confidence interval. So perhaps we picked an X bar right here. And if we were lucky enough to do that, then the population mean does fall within that interval that gets created around X bar. So we find the confidence interval that surrounds the sample mean with this formula. We take X bar and we subtract Z times the standard error. And that's on the bottom end of the range. And then on the other side, the top end of the range, we take X bar and we add Z times the standard error. And that will give us our confidence interval. The Z-score that we use for a 90% confidence interval is negative 1.645 and positive 1.645. So we'll use that here with the negative Z and over here for the positive Z. So the problem gave us an N of 36, an X bar of 2,630, and a sigma of 600. So using all that, we plug that into the formula to calculate a 90% confidence interval. We're trying to estimate the true mean cost of a hospital stay for all patients at this hospital. So we N equal 30, X bar 2630, sigma is 600. A confidence level of 90% means that we're using a Z of negative and positive 1.645 in our formula. So here's our formula again. We're going to plug in those values and calculate the confidence interval. So let's say 2630, that's the X bar, and here's where we use the negative Z-score, minus 1.645 times 600 divided by the square root of 30, and this is the range, so this is the upper side now. 2630 plus 1.645 times 600 divided by the square root of 36. So I'm going to do this with you on the calculator, and we're going to get an answer here, and that will be our confidence interval. Okay, so with me, try this. 2630 minus 1.645. And you don't have to put the parentheses. It's automatically, the order of operations is maintained because we're multiplying by 600 and dividing by the square root of 36. If we do second square root, we'll get the square root symbol, and here we'll put 36. So adding parentheses around the 600 divided by the square root of 36 is optional, but it won't change the calculation here. So that's the lower end of our confidence interval. We're going to hit enter here and get the answer. And then it's really easy to just repeat that last entry, second entry, and just change the subtraction to an addition. So here we use that positive Z-score, and we got the other side of the confidence interval. So our range goes from 2665.5 to 2794.5. Okay, 2465.5 to 2794.5. And these are estimates in US dollars. So we have the dollar sign there. Now, the next step is to interpret what this confidence interval means. So we can calculate it, but then we also want to express it in words. We're going to say that we are 90% confident that the true mean cost of a hospital stay for all patients at this hospital is from $2,465.50 to $2,794.50. So we always state our level of confidence, and we state what we're trying to estimate. We're trying to estimate the true, and you may even want to add in here population mean to really stress that we're estimating the mean of the population. That's what we don't know. And then we state what it is we're measuring. In this case, it's the cost of a hospital stay. And then we state our confidence interval. So let's visualize this confidence interval. In the center, we have our point estimate, 2,630. On the right side, the left side, we have the low end of our confidence interval, 2,465 and 50 cents, and 2,794.50 cents on the high end, upper end of the confidence interval. Now, what if we were to take our sample size from 36 and increase it to 80? So imagine what happens to the sampling distribution when we increase our sample size. When we do that, the standard error, which we've seen in the formula, and we've also seen it visually using Desmos. When we increase the sample size, the standard error, which is this formula, the standard error decreases, and that's because the denominator increases in this fraction and gets bigger. So we see that the standard error decreases. We see that the sampling distribution gets more clustered about the mean and more narrow. So what's going to happen with this confidence interval with a smaller standard error is that it is also going to become more narrow. So if you were to plug in 80 into that formula instead of 36, you're going to see that the arrow is going to shrink that we create. So the numbers 2519.65, 2740.35. So if you draw that arrow, it's more narrow than the original that we calculated up here. And that's what we get with a larger sample size. Okay, increasing the sample size makes the confidence interval more precise, which makes it more narrow. So there are the confidence interval formula for 90, 95, and 99% levels of confidence are almost all the same. The only thing that changes between them are the z-scores that we use. The confidence interval formulas are all the same. The only thing that changes between the different levels are the z-scores that we use. So here are the formulas with the differing z-scores. So for a 90% confidence interval, we use the z-score negative 1.645 and positive 1.645. For a 95% level of confidence, negative 1.960 and positive 1.960. And for a 99% confidence interval, negative 2.576 and positive 2.576. These can either be memorized, which I don't recommend, or just write it down and have it available to you when you take your exams. Okay, the next thing that we're going to look at in a confidence interval, we are going to do another example, but first I want to talk about the width and the margin of error, because the margin of error was one of the things that was um, that was stated at Gallup.com that gave us a clue that we were working with a confidence interval. When you are provided with a margin of error, a range of values is created around the point estimate, and that range is the confidence interval. So the two values that we construct when we build the confidence interval are the lower limit and the upper limit. So in this example that we just finished, 2465.50 is the lower limit and 2794.50 is the upper limit. So I'm going to make a picture here for the lower and upper, and the difference between the lower and the upper is called the width. So if we take the upper and subtract the lower, 2794.50 minus 2465.50, we get the width of this confidence interval. So visually, this length here is the width. Okay, in this case, when we subtract these two numbers, the width comes out to be $329. So that's not the end. After we get our width, just a second, in the very center of our confidence interval, we have our point estimate that was provided to us in the beginning of the problem. We were provided with that X bar. The width is half, I'm sorry, the margin of error is half of the width. So if we take the width of the confidence interval that we just did by subtracting the high upper limit minus the lower limit. If we take that width and divide it by 2, we can get the margin of error. So we take our 329 and divide it by 2, we get a margin of error of 164.5, and we put that on the left and right sides of the point estimate. On the left side of the point estimate, we're subtracting 164.5, and on the right side, we're adding 164.5. So what this is telling us is that if you start with a point estimate of 2630 and you subtract a margin of error, you get to the lower limit of the confidence interval. If you add a margin of error to your point estimate, you get to the upper limit of your confidence interval. So we can express our confidence interval in two different ways. We can say that lower limit to upper limit is our confidence interval, or we can also use the notation of the point estimate plus or minus the margin of error. This is the point estimate, x bar, and this is the margin of error, plus or minus, and I'm just going to abbreviate it with ME, margin of error. So this is lower limit, upper limit. If you see a problem referring to a confidence interval in the first way, realize that it can also be referred to in the second way. They are interchangeable. They're just two different ways of expressing the same thing. Okay, we're going to look at another example from beginning to end, and this time I'm going to go through without those longer explanations of each part. A medical device manufacturer produces blood pressure monitors for home use. The company wants to advertise the average lifespan of their monitors before recalibration is required. Many healthcare professionals recommended recalibrating monitors when their accuracy falls below a threshold. So that's some background information that doesn't give us the numbers that we're going to need, but it provides a context for this problem. To determine the average lifespan, a random sample of 100 monitors is tested. So I'm going to write down the information as the problem presents itself. And the mean lifespan is found to be 170 months. So a sample of 100 has a mean of 170. That means X bar is 170. That is going to eventually be the point estimate for our confidence interval. Assume the lifespan of these monitors is normally distributed with an unknown population mean and a population standard deviation of 30 months. So remember, mu is always unknown in a confidence interval. That's what we're trying to estimate. Sigma is provided here as 30, the population standard deviation, which is going to become needed when we go to the formula and we put that standard error into the formula. Find and interpret a 95% confidence interval for the population mean lifespan of the blood pressure monitors. So what we're doing is using a sample of 100 of these monitors, and we're trying to estimate the population mean lifespan of blood pressure monitors based on the mean of the sample. We're going to also calculate the margin of error for the confidence interval, and we're going to do the same thing again, but we're going to change our confidence level from 95 to 99. And then we're going to visually compare these two confidence intervals and explain how each provides a different level of confidence. What are the benefits of using a 95% confidence interval versus a 99% confidence interval? Okay, so let's start with what we are provided. N equal 100, X bar is 170, sigma is 30, and for the confidence level of 95, we want to remember that our z-score is 1.5. 1.960. That will be a negative on the left for the lower end of the confidence interval and a positive on the right for the upper end. Okay, so we're going to use the negative z over here and a positive z over here, and here's our formula. Let's plug into our formula. So we put in 170 for the x bar minus the z-score minus 1.960 times sigma divided by the square root of n. And then the upper end, upper limit of the confidence interval, x bar plus 1.960 times sigma divided by the square root of n. So this is the part where we're going to go to the calculator and evaluate this. So let me go and open up my calculator. So let's plug in 170 minus 1.960 times, and this we're going to do 30 divided by the square root of 100. Get our answer for the lower limit, and then repeat that, changing the minus to a plus to get the upper limit. Okay, now this is measuring months. This is months that these monitors can work before needing to be recalibrated. So the range of months is from 164.12 to 175.88. Now, while I'm here, I'm also going to calculate the margin of error. We're going to take the high end of the confidence interval, the upper limit, subtract the lower limit, get an answer, and then divide that answer by 2. So our margin of error is plus or minus 5.88 months. Okay, so we have our confidence limits, 164.12, 175.88, and we have our margin of error, 5.88 months. To interpret this, we're going to say that we are 95% confident that the true mean lifespan for these blood pressure monitors is from 164.12 months to 175.88 months. Visually, we have the low end of the confidence interval on the left and the high end on the right, an arrow in between, and directly in the center is the point estimate 170. And here's how we calculate the margin of error. Again, we did it on the calculator already. If you want to do this on the calculator in one step, you can use parentheses. So 175.88 minus 164.12, and then divide by 2, plus or minus 5.88. So if we visualize that margin of error inside the arrow, we add 5.88 to get to the upper limit, and we subtract 5.88 to get to the lower limit. So starting with 170, add a margin of error and subtract a margin of error. So our confidence interval could be written in either way. We can either write it 164.12 to 175.88, or we can write it as point estimate plus or minus 5.88. Doing this for a 99% confidence interval is the same thing, except we change the z-score. For a 99% confidence interval, the z-score we use is 2.576. So we go back to the formula, plugging in everything the same except the z-score, and then we go to the calculator. So we plug in here 170 minus 2.576 multiply by 30 divided by the square root of 100. Sometimes the square root is nice and easy to do, and you could do it in your head, and other times it's not. So I'm just using the formula as you would if you had um, an odd number for your sample. So 1.6227 on the low end, we're going to round to 2 decimal places. And let's do this again and change the minus to a plus. Okay, 177.73 on the high end. Actually, going back to my slideshow, I'm seeing that I don't round, so let's keep it to the 3 decimal places. I'm going to calculate the margin of error with all the digits that we have shown here. 177.728 minus 162.272. This time I'm going to do this margin of error on one line, 7.728. So if I choose to do this in one step, I have to wrap the numerator, wrap the subtraction in parentheses. So let's go back. Okay. So I have our confidence interval, and to interpret this confidence interval, we state we are 99% confident that the true mean lifespan for these blood pressure monitors is from 162.272 to 177.728 months. Okay, so here's the visualization of the confidence interval for the 99% confidence level. Take that margin of error and put it on the left and put it on the right. Starting with your point estimate of 170, you can add a margin of error to get to 177.728 and subtract a margin of error to get to 162.272. So we write x bar plus or minus the margin of error. And that looks like 170 plus or minus 7.728. So these are the two confidence intervals side by side, the 99 and 95% confidence levels. So the level changes, and what happens as the confidence level changes? A few things. The margin of error changed. So in a 95% confidence interval, it was negative and positive 5.88. In a 99% confidence interval, it was negative and positive 7.728. So it looks like when our confidence level increased, our margin of error increased. The other thing that changes is the confidence interval widens. With a 95% confidence interval, we see a more narrow estimate, and with a 99% confidence interval, we see a wider estimate. So what changes with an increase in confidence? We just talked about it. But what are the benefits of using a 95% confidence interval versus a 99% confidence interval? Well, because you would think that a lot of students think that a higher confidence is better because it means that you're more confident in your answer. And while you are more confident in your answer, it's not necessarily always better to have a wider confidence interval. Having a wide confidence interval makes your answer or makes your estimate a little bit less targeted. So imagine your school, and imagine that you're trying to find somebody in your school, and suppose you were told that the person is in the school. So that's a pretty big place to look. But then let's suppose that you were told that the person is on the second floor of your school. Okay, so I'm getting a little bit more narrow as to where the person is. And then suppose you were told what room the person is in. So now you got a real targeted um, location. That's like what's happening with confidence levels. Even though a 99% confidence interval gives you most confidence, like the person is in the building, that's the most confidence. It doesn't necessarily help you so much because it's not so targeted. If you want a targeted answer, you go with a lower confidence interval. So a lower level, 95% gives you the more targeted estimate. So we see width and margin of error increase as confidence level increases, but the narrower interval, the 95% interval, provides more precision. The wider interval, 99%, offers greater confidence. So it's a give and take as to which level works best. A lot of times people go with the 95%. It's one of the most common confidence intervals that we use. But all three are going to be helpful. We're going to remember the z-scores for all three of these, or write them down and have them available so we can construct our confidence intervals. And that's it for this lecture. The next lecture, we're going to continue with confidence intervals, but there's going to be a slight variation in the way the problem is presented to us, and that's going to change the approach that we take. So I hope this was helpful, and I will see you at the next lecture. Bye.